Okay, so it's a great pleasure to have Xiaoliang Qi from Stanford here today to talk to us about the entanglement island, the miracle operators, and the firewall. So go ahead, Xiaoliang, whenever you're ready.
Okay, thanks, Jamie, very much for the invitation and introduction. My understanding is this is the audience is very familiar with topics, the entanglement island and related things. So I'm going to probably be a little quick on the introduction part. And I hope to have a lot of discussion. So please feel free to stop me anytime if there's anything unclear. So this is based on a recent work I posted on our archive a few weeks ago. So I will briefly overview what is the motivation, and then based on some calculations based on the entanglement island and replica wormhole calculations, I would like to discuss how to discuss a formula about state reconstruction in the case of evaporating black hole, and then see that there is a contradiction if we try to apply this formula to a general dynamics of the radiation. And then so from there, that's what leads me to name these miracle operators, which means there are basically two kinds of operators. There's regular operators, and then there are the miracle operators, which if you measure them, you're changing the geometry. And then I'm going to make an explicit construction of them and discuss the implication in the firewall paradox. So roughly speaking, the black hole information paradox comes from unitarity of quantum mechanics and how it's how to understand that in the gravitational systems. And so that there's two kind of paradox. I think so. I mean, please let me know if you have any comments about this. This is my naive understanding. I'm not in this field for too long. So my understanding is that there is the older paradox, which just talks about how like you can have a black hole that's evaporating, and then how all the Hawking qubits looks thermal, but the entropy of the whole system should go down eventually, because if you believe in unitarity, a pure state matter from black hole should become pure in the end. So that's summarized in this page curve, and that's what is I think we can consider that paradox as being resolved by this recent works on entanglement island. And then there is the other kind of paradox, which so known as the AMPS paradox, or the firewall paradox, and that's different from the first one, because it talks about the interior, talk about what happens for infalling observers, and in the setup in this picture here, you can consider Hawking radiations, and then the later radiation B after the page time seems to be entangled simultaneously with its partner in the interior, B tilt, and also with early radiation A. The reason why it's entangled with early radiation A is that the entropy is already going down. So there is a negative conditional entropy, means SBA is smaller than SA. And that seems to be contradictory with the monogamy of entanglement, because it seems like B is entangled with two things at the same time. And yeah, so that's just to quickly sketch what is the firewall paradox. And the question now, what I want to understand is, now we have this understanding of the page curve based on the replica wormhole calculations. Then what is the implication to what the falling observers see? So that's one. That's one of my motivation. Before going there, we will try to discuss how the state reconstruction works in the replica. I will start with an overview of the replica wormhole calculation, although it will be quick because I know you're all very familiar with it. Yeah. So in particular, yeah, just one sentence on the slides. I just want to mention that, yeah, like in the firewall case, the concrete questions we want to understand is like, can I do some measurement completely in the exterior? And as a consequence of that measurement, the entanglement between B and B tilde is destroyed. So the entanglement across horizon is destroyed, and that's what the firewall means. And then the other question is like, can I check the entanglement between A and B, and then jump in to check the entanglement between B and B tilde? Right, so these are questions that hopefully with the that we are hoping to get some more concrete way to see them, like to make the discussion more make the discussion less ambiguous. Okay, so I will start with this setup of the replica wormhole. So the model I will consider is an ADS black hole coupled with a flat space thermal bath. Well, a flat space bath. I don't mean the bath is in thermal equilibrium. It's just a flat space system. And then, if this is a quantum field theory in curved space, then when we calculate the entropy of a region, we will do the replica trick and take n copies, and then we will introduce a branch cut around the boundary of A. So that's the standard thing we do in quantum field theory. And then the only difference here is that the geometry in the ADS part is fluctuating. So we allow the geometry to be in quantum zero positions. So you have a path integral on the geometry of the GB, which is the black hole part, and then the GR is the flat space part, which is fixed. So then when we calculate the entropy of a region A in the bath, then you introduce this branch cut. Like we have multiple replicas which are connected through region A. When you go around the boundary of A, you go to the other replica. And then because the black hole part is allowed to fluctuate, then there is a sum over different topology. So you have this possibility of having this replica wormhole where there is another part of another region I in the ADS space where you also have a branch cut connecting the different replica. So, and then based on this general setup, then the only assumption you need to go further is the assumption that your path integral in the gravity system is dominant by a saddle point. So if we assume the geometry path integral is dominant by a saddle point, and the saddle point is symmetric under cyclic permutation of different replica, then you could get this basically the possibility is reduced to two kind of possibilities, whether there is either there is no wormhole connecting the different interiors, the different interior regions, or there is a replica wormhole, in which case, if you look at the partition function, it looks like a curved space QFT partition function of a different region, which include the red line here, which is A region, and then include the interior region. That's at the boundary of the wormhole here. So that's like the I, and this is the A. So now if we assume the saddle point is replica symmetric, you can take the n goes to 1 limit and get this extremal surface formula where we should extremize this generalized entropy. So in terms of quantum states, then I want to clarify some conventions that we need to use in the following. So we are thinking of this formula should be considered as a mapping between two different systems with different Hilbert space. One system is the quantum field theory, which is defined on a given manifold. So I have a Hilbert space of quantum field theory once I give you a space-time geometry M, and I also need to give you a Cauchy slice, but the different Cauchy slices should correspond to the same Hilbert space. And then the other Hilbert space, what I call HQG, is the quantum gravity Hilbert space, which means the ADS boundary together with the quantum field theory in the bath. So that's like the complete, like the real physical degrees of freedom. So for example, if I think about an SYK model as a toy model of the ADS part, then the bus is like, say, let's say some free fermion system. Then that will be the HQG. And then the HQFT will be like the quantum field theory in the curved space coupled with the flat space. So then when we fix an M, which is a saddle point manifold, then we are embedding these quantum field theory states to the HQG. And that embedding also is given by this manifold. Any questions so far?
So just in the blue box, HB and HR are the boundary degrees of freedom that are dual to the gravity, and then the auxiliary system.
HB
right?
is the boundary, yeah, the boundary of the AES.
Okay.
And the HR is the radiation.
Okay.
But I think exactly one subtlety is whether we can say HB is the one that's due to gravity. I mean, I think that's the. So I mean, I would like to. I think it that way, but then I think that seems to be part of the problem. But I think there is no question that in this level, like when I think about the whole HQG, it is it's tensor factor, it's tensor product of HB and HR.
Yep.
And then when we map the HQFT to this, if we think of it in the ADS-CFT way, then I would have thought the mapping, what happened is HB had a code subspace, that's the ADS part, and then HR is just HR. And then so in terms of notation, I would like to use these bold letters, bold fonts, the Greek letters to represent states in the QFT, and then the regular letters to represent the HQG states. The boundary, you can think of them as like box states and boundary states, but here both of them coupled to the back. And then, so just one comment that will be important later is that, as you can see, to have a non-trivial entanglement island, I need this contribution of the generalized entropy, which is SAI in QFT plus the boundary area of I. I need that to be smaller than SA itself. Otherwise you will get a trivial saddle point SA. So in order to have an island, you have to reduce entropy by introducing the island. And that has a almost trivial consequence, which is the SAI must be smaller than SA. And that means that there is a negative conditional entropy between A and I, which is telling me that there is quantum correlation between A and I. It's impossible to have that if you have just some classical correlation. And more precisely, classical correlation means this kind of separable states. If you consider a region I, and in the QFT, oh sorry, these fonts here, these letters here should all be, these should be all like in the QFT, so they should all be thick. And so in the QFT, if you have the state of A and I which is separable, then SAI will never be smaller than SA. So you will never have an island for a region like that. So that tells you that whatever like for a region to have an island, the necessary condition is there is quantum entanglement between A and I. Okay, so now we want to discuss how the state reconstruction works, and this is really in parallel with the JLMS construction in the ADS-CFT case. So the idea is that if we have this saddle point that dominates the calculation of trace rho to the n, then we can consider two states rho and sigma, which are very similar, and their energy is only different of order 1. And in that case, the rho and sigma correspond to almost the same saddle point. So if you calculate this kind of cross terms, where is my? Oh, sorry. Here. If you calculate this kind of terms, I think I should put a 2n here just to be consistent with what I'm writing in the next slide, in the next line. But basically, the point is that this is given by the same saddle point as saddle point as trace row to the trace row A to the 2n. Like you change some rows to sigmas, it doesn't really change the geometry. So if I believe there is a manifold that gives you dominant contribution to trace row to the 2n, then the same manifold should contribute to this. And therefore, if I look at a norm distance, a 2n norm distance between these two states, the trace row minus sigma to the 2n, if I look at the 2n norm distance, then it should, because each term here is given by the same manifold. So overall, it should be given by just replace each term by rho and sigma in the Q of t, but now it has AI because there is a branch cut also at I. So now you just replace A with AI and then replace the state rho by the Q of t states. And then there is a contribution in front, which is the contribution of the geometry term, the Einstein-Hilbert action. And we know that when you take n goes to 1/2, which means, so now if I take 2n goes to 1, then this is like when the conical singularity goes back to trivial. Then in that limit, this an will be something proportional to 2n minus 1 times the area, something like this. So when we calculate the entropy, you take a derivative, and this is the contribution to the area law term. But here we're just calculating the norm difference. We're just calculating the one norm. So I'm taking the rho minus sigma to an even power, and then take that even number and then continuating to 1. And in that limit, this contribution of the area law goes to 0, and then we get this equation in red here, which says that the two states has the same one norm difference in the QLT and QD. And in the GMMS, there is an equation which is about the relative entropy, and it's based on the same kind of replica calculation. So here I prefer to use one norm, but the derivation is really in parallel. Any questions about this?
Let's see. I'm not sure if I have a precise question. I think the question is, so these little row, or so the rows on and sigma in the first equation, or I guess the fourth line, these are in the microscopic quantum gravity theory.
Yeah.
I'm just wondering the U is somehow in the, I guess I'm wondering what it's not totally clear how I define this action of the unitary on the interior.
Oh yeah,
in that
sorry,
picture.
I mean,
are you assuming something about that?
Yeah, so that's an example of two states which are very similar. So this formula is, so the discussion here should apply to general case where I have two states which are which has very close energy momentum tensor. And one in this particular example I'm considering here is if you have a particle in the interior, and then I apply the unitary that applies only to that qubit, which is like for example flipping the spin of that qubit. So like in this example, like rho and sigma both contain this pair of particles which are entangled, and then I apply this UP, which is say flipping the spin of the B tilt, which is in the interior.
Yeah.
Let's say this is B tilt, but that's just an example. And for this discussion here, I don't really need any special details there. But the point is that at the level of Q of T, this is totally well defined. So like if I define, I say I have rho, and then I have sigma, which is obtained by let's say sigma AI is like rho AI, and then apply the UP. So at the level of Q of T, this is well defined. And then the macroscopic states, I'm assuming, I'm defining these macroscopic states as just the states corresponding to these Q of T states.
Yeah. Okay.
So it's like I have this setup. I have this spin flip in the bulk, and then I now if I only access the region A, and then say let's take these two states, and then if you allow me to take a product of them to some power, and then take a trace, then what's going to happen? So basically, the rho A here, rho A and sigma A are defined by these QFT states.
Okay.
And then the conclusion is that if you take this analytic continuation, you conclude that whatever one norm distance you have between the QFT states is preserved for the macroscopic states. So this is really a statement that there is actually there is a unitary mapping. That there is a norm preserving mapping from the QFT Hilbert space with that manifold M to the QG Hilbert space.
Thanks.
So we could also say we just use JLMS on the relative entropy, and then you show that the relative entropy is preserved. Then there is a reversible channel. There is a reversible quantum channel that map between these states, and therefore the norm distance will all be preserved. So this is just a more direct way to prove the same thing. Okay, so this state reconstruction formula looks pretty natural. It's just generalizing the ADS-CFT case to the only difference from ADS-CFT is now we have a region A that's defined in part of the bus rather than part of the boundary. And then, okay, but we are going to see that if I assume this formula holds generally, then there is some problem. That's what I want to get to. Okay, so but before that, let me say what's interesting. One thing that's interesting about the one norm difference. So compared to other norms, the one norm is nice because it tells you how you can distinguish the two states optimally with one measurement. It tells you how much you can distinguish the two states if you only measure one thing, but you have you can choose what operator you measure. And it's very explicit because you can just take rho minus sigma as the matrix and diagonalize it. Then you get some eigenvalues, and some eigenvalues are positive, some are negative. Then you just take the projector PA to be the projector on the positive eigenvalue. So which means like you can define the ZA, which is like the same eigenvectors as rho minus sigma, but the eigenvalues are replaced by the sign of lambda. So just positive ones and negative ones. The positive ones replaced by +1, negative one replaced by -1. And then PA is just 1 plus Z over 2. So it's projecting on the positive lambdas. And so that's some operator that commute with rho minus sigma. And if you calculate the expectation value of that operator, then that's equal to the half of the one norm distance. So this is, and if you choose any other projectors, it will be smaller than this number. So this is telling you that there is an optimal measurement PA, which is, if you measure that and then compare the expectation value of that operator in rho and sigma, then the difference is the one norm distance, and that's the upper bound of how much you can distinguish the two states with one measurement. So that means that this one norm equation, this red equation here, tells you that like if rho AI and sigma AI are different by a spin of a particle in the interior, then of course I can do a measurement in the QFT case that distinguish them. Then this equation tells me that I can do the same in the quantum gravity case in the exterior region A. So there must be this operator PA which can distinguish the two states if there is a one norm, there is order one norm difference. Okay, then now there is a there is a consequence of this. So let's consider a special case for the radiation. So we want to apply this. So the point is that this derivation doesn't seem to depend on details of the radiation dynamics. So it seems the only thing we have assumed is that the path integral of the replica system has is dominant by a saddle point, and the saddle point preserves the replica symmetry. So we don't need to assume that saddle point itself, like how different it is from the original geometry. And it could backreact in different ways, but as long as we assume there is a saddle point and the saddle point preserves rotation symmetry, then we get this kind of formula. So now since it doesn't seem to depend on details of the dynamics of the radiation, we can consider a special case, and there seems to be some conflict there. So the special case is when we have part of the radiation that's labeled W here. Let's consider. So I'm considering R1 and W together as the radiation system, and as the bath system, and then that contains the ordinary like Hawking qubits, which is R1, and another subsystem W, which is like your lab equipment that you are measuring the Hawking qubits. But I could include that as part of my radiation system. So I'm considering a case just like if we have a radiating black hole and then we are sitting there and measuring the Hawking qubits, but we are ourselves is part of the radiation system. So everything is unitary, but the unitaries here, the dashed lines here, are doing some coupling between the Hawking qubits and the lab equipment. But the point is that when that coupling is not if that coupling is not quantum, like if as we do in most physical experiments, we're just doing measurements. We're getting some classical measurement result and write down them. Then these are called LLCC. These are local operators and classical communication. So in these cases, we never had any quantum entanglement between our lab equipment W and the radiation. So if I consider such a situation, then as I mentioned earlier, that means that W has no quantum entanglement with anything else, and therefore it has no negative conditional entropy. So that means if I think about this path integral and ask about the entropy of W, so now I'm not asking about the entropy of A. So I consider a case where A is a region with an island. So now W has some general coupling with the radiation system, and then I'm measuring W. I'm calculating the entropy of W, the trace rho W to the n. Then because it always has positive conditional entropy with any other region, then you will never have an island. So you conclude that W have no island, and therefore you will get a this equation. Well, you will get an equation that says that rho W minus sigma W, the one norm distance, will be the same as the Q of T quantity. So let me be more specific. So a special case of this LLCC is a single measurement. So let's consider a case where I have a W that's just doing a particular measurement on this region A, and then that in particular I want to consider that measurement to be this PA, this optimal measurement, and then I do that measurement as binary. It just gives me an output of 0 or 1, and then I record that result on W. So if the state on A is in the space of PA equals to 1, then W goes to state 1. If it's in the state of PA equals 0, W will go to 0. So that's what this UM do. So I draw another ancilla W tilde because we needed to trace over the other ancilla, and after that you have only classical correlation between W and A. So like when you do a measurement and then you write down the results, you usually write down many copies, and as long as you don't look at the entire copy, then there is no quantum entanglement. But that's just to be very explicit. I just want to clarify that the whole thing doesn't need anything non-unitary. So although we are saying measurement, but you don't need anything non-unitary. So we will get a state W that's classically correlated with A. And then therefore this argument applies, and we will conclude that W have no island. But then there will be a contradiction, because If W have no island, then if I apply a unitary in the interior, then in the Q of T, I will conclude that rho W and sigma W are the same because I'm just tracing over things that are space-like separating from me. Right? So if I apply a unitary in the interior, it's space-like separated from the entire radiation. So I will conclude that in Q of T, rho W and sigma W are the same. But that implies that if W have no island, that implies rho W, that implies this equation, the blue equation here. Like rho W minus sigma W has 0 one norm distance, because what happened in the interior is space-like separate from me. And so I cannot conclude that for a region like A, because that equation will involve the interior, because if some region has an island, then the right side of this equation, just like the red one here, for region A, then you're going to have the Q of T stays in a bigger region, and that allows you to know things about the interior. But the region like W doesn't have that ability because it doesn't have an island. So if this formula works, then we will get that the 0 difference. But this is apparently wrong because W can know what happened in the interior by measuring A.
Sorry, I had a question.
Yeah.
So if you, yeah, I think what you're discussing on the last slide, or maybe one more back.
Yeah.
This one, yeah. So I guess your suggestion is that you're doing the measurement, what we'd say coherently, right? So you're keeping everything, you're not tracing anything out, right? So that everything's unitary.
So it's if I include everything here, it's unitary.
But if you do that, then I think you do entangle the two systems.
Yeah, so that means that if I look at W2 together, it has a quantum entanglement with A.
Yeah, yeah.
Although it's still not much, it's just one bit of entanglement with A. Yeah, but that's just like in the radiation system, you can look at different subsystems. Some has a quantum entanglement, some doesn't. So when I calculate the entropy, I can calculate the entropy of W tilde or W, and here the statement is that if I only calculate the entropy of W, I will never get an island.
Oh yeah, okay, that sure, yeah.
Yeah.
Okay.
So in other words, the problem is that usually we will think that there's no problem because sure, of course there's some regions that doesn't have any quantum entanglement with the interior. Like I can just take a small region, and then there is no much entanglement with the interior. That's not surprising. And if I tell you that such a region will know nothing about the interior, it's not surprising. But that's just can't be true, because in this case, like if W is measuring A, then actually you could show that if you are doing that optimal measurement, you will get exactly the same one norm difference after the measurement on W. Like whatever A knows about the interior from the one norm distance, W will know after the measurement. That's the consequence that one norm distance is measuring the optimal measurement result. So so that's something classically, that's something you can do classically. You don't need to like entangle with that system to do that. So you can do this simple derivation here, which is saying like if you trace over that W tilt, then the channel applying to A and W is just like this. Like you take rho A, and if it's projecting to PA equals to 1, then W has state 1. If it's state in orthogonal projector, W is 0. And then you can ask, okay, what is rho W after this? I just trace over A, I get rho W is like this, where P is the expectation value of PA. So from that, you can, if you do this for two states of A, so the input state of A is rho, you get this. Input state is sigma, you get this, where P is trace PA times sigma A. Then you look at what is the one norm distance between rho W and sigma W, the output state here. You look at the point is that if you have two input states rho and sigma with certain one norm distance, then the two output rho W and sigma W have the same one norm distance. So that's just quantitative way of saying like W has to know something, because if A knows that, I could do that particular measurement, and then W knows it. and that's what is in contradiction, because it seems like we get this equation from the fact that W has no island, and if W has no island, then this Q of T quantity will be equal to 0, because in Q of T there is the interior is space like separated from me, so a unitary there will not change my state. On the other hand, this explicit calculation tells me that the rho W minus sigma W will be equal to what happened to A, and that's not 0. Yeah, so where is the problem? Yeah, or maybe, yeah, before asking what's the problem, is there any other questions about the contradiction here?
So the map into W, like by measuring and then tracing out W tilde, it only preserves the distance between rho and sigma, right? Like it doesn't, like the measurement you did was dependent on the two states that you're considering.
The measurement, yeah. So, but this equation holds for any two states.
For yes, so
yeah,
for
this equation holds for any two states. Like
yeah.
any two states you put in, then one norm distance that's passed to W, and W get the same one norm distance. That optimal measurement depends on the states.
Yeah.
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 So like, yeah. So like, let's say I flip the spin in the interior so that I just can't find my cursor. Yeah. So there is a spin flip in the interior. So in the Q of T, AI has an non-trivial one norm distance between the two states, and then there is an optimal measurements that can tell you that because of this, because this rho A minus sigma A is order 1, so there is an optimal measurement PA. Yeah, so I would like to use that optimal measurement. Yeah, but oh yeah, sorry. Yeah. Sorry. I was confused. Yeah. So this works for any two states, rho and sigma, but only if you are doing that optimal measurement. Yeah, and the measurement depends on the state choice.
Yeah.
So in general, I think that is probably an inequality. In general, if you are doing a wrong measurement, then you will get this. You will get like rho minus sigma will be smaller for W. You lost some information.
Yeah.
Yeah.
Anyways, I'm not sure if that matters later. I just was clarifying.
Yeah, I think it's yeah. Certainly it's important that this optimal measurement depends on the states.
Okay, thanks.
Any other questions? Okay, so it seems that there is this contradiction, and then where is it from? If we go back to the whole reasoning, it seems that everything only depends. I mean, everything depends on this formula, and this formula just comes from the state reconstruction formula. It just comes from the assumption that the gravitational path integral, when you calculate trace rho to some power, like when you calculate trace rho m and sigma to n minus m, the only assumption we need is that when we calculate these kind of things, it's dominated by a saddle point that's a smooth geometry and respecting replica symmetry. So it must be that assumption is wrong. So this is saying like when we consider this kind of particular dynamics, like when your dynamics contain this kind of UM, then if I try to calculate entropy of W after that, at least in this situation, you shouldn't assume this. You shouldn't make this assumption, which looks very reasonable, but it tells you that like if I assume, so just want to clarify, like I'm not saying like, okay, when you apply this UM, it leads to some back reaction, so you get a different geometry from the case without the UM. That will be not surprising. Right? I mean, you need to do this big measurement. It's going to cause you some back reaction. But the surprising thing is that it tells you that you can't even find a different saddle point which works. as long as that saddle point is this smooth geometry with the flat space at the boundary condition and then preserve replica symmetry. Just saying nothing like that will work, because if that works, it will just give you some island. Maybe it will give you a different island as you expected, but if you take the attenuation, it's going to give you that one norm, that state reconstruction formula.
Sorry,
yeah.
So you showed, or you argued earlier that there's this calculation showing that if there's an island, then this trace distance is big. But is it clear that the reverse is true, so that if there's no island, then the trace distance has to be 0?
So the argument is that if there is no island, then I can do this calculation in QFT. Then that means I could, like the blue equation here. If there is no island, if there is a region, let's say, I mean, we don't need to think about this kind of exotic coupling. We can think about just a small region here, right? Let's say A prime. Then there will be no island. Then that means that when you calculate rho A prime, you trace over everything else, including the interior. When you calculate the QFT rho A prime. So if you have a unitary in the interior, it's not going to change rho A prime. Means it's in the complement.
Yeah, I guess it just seems like it's strange to me, because you've taken A, you've measured it, figured out exactly the piece of information you're looking for, and then stored it in A prime. And so now it's less clear to me that should be small.
Yeah, so basically what this is saying is that so on one hand, it seems totally reasonable that you could do a measurement in a bigger region and then get this one bit of information and send it to a smaller region.
Yeah.
On the other hand, you have to answer like where during this process I went beyond QFT, because this like if I'm applying this island formula, like again, my assumption is the saddle point calculation. So if there is a saddle point calculation, it tells me that I could do everything in the QFT as long as I'm choosing the right region. So the point is that this replica wormhole calculation tells you that when you calculate some quantity like trace rho to the n, that's equal to something in QFT as long as you enlarge the region with I. So if you have a region with no island, then it's just saying that the trace rho to the n is the same as the QFT quantity. But in the QFT, then the interior is like separated from me, so I shouldn't know that's being put in.
Let's see.
So of course, I mean, on the other hand, if say it in another way, it just means that whenever you can extract some information from the interior, you have to go beyond that causal structure of QFT. And that's of course not surprising, but this derivation is telling me that in order to do that, something must be wrong in that replica. So in order to do that, this replica wormhole calculation has to be done differently, because means it cannot be dominant by that kind of saddle point we considered before. Otherwise, it will not happen.
Okay.
By the way, how long is the talk usually?
I think, I mean, it's nominally an hour, but I think we're flexible on time. So you shouldn't feel too rushed since there's been lots of questions.
Great, thanks. Yeah, so basically, so far, this is like the first half of the talk, but I won't be going too long. But basically, the first part of the talk, the message is that there is a conflict, and that suggests that whenever I can do a measurement that's smart enough to know anything about the interior, that has to mean that after that measurement, if I'm doing a entropy calculation, even to a small region, that has to involve some saddle point that's different from the kind of saddle point that we consider. Which means it's a smooth geometry with a flat space as boundary condition and preserves the replica symmetry. And then, so the next part is I'm going to just give some explicit example of such measurements, and that's natural. That's something natural coming from this optimal measurement based on the one norm distance. So as I said earlier, when you have the one norm distance, then there is a optimal measurement PA. So it's more convenient to look at the ZA rather than PA. And ZA is just having the eigenvalues plus minus 1 rather than 0, 1. So the eigenvalue, so ZA is an operator that has the same eigenstates as rho minus sigma and has the eigenvalues plus minus 1. So I could cook up a replica calculation for ZA itself. I can write down an odd power of rho minus sigma. And then if I take that odd power back to 1, back to 0, that will give me the ZA. So the odd power will have eigenvalues that are lambda to some power 2n minus 1. So if I take 2n minus 1 back to 0, I will get the sign of lambda. Okay, so that means that I could define operator ZAK. So let me use K rather than N to be consistent with what I wrote later. So I can define this operator as ZAK. So if I take K go back to 1/2, then go back to the projector, the ZA operator. But this ZAK is itself, of course, depends on states because this optimal measurement depends on states. So when you do this, you see explicitly that when we calculate a quantity like this, when we calculate a quantity like trace of ZAK with rho A, then there is replica wormhole. And that's in this particular construction, we see this is the way that the calculation goes beyond the assumptions we did. Although it's the same kind of replica wormhole mathematically, but physically it's going beyond the assumption that we were thinking like there is n copies of the system and there is wormhole connecting them. Instead, we need wormholes connecting with the operator. So just to go a little further on what happened if I have this, going back to that setup we have earlier, like if I draw this diagram. So we are considering the case where I have this region A, and then I'm measuring region A with a W. And now if I replace that measurement PA by the replica version, so if I replace that PA by PAK, which is like 1 plus ZAK over 2, and ZAK is that odd power of rho minus sigma. So that's not a projective measurement anymore, it's like a weak measurement. But it's still something that you can achieve by a small and theta W. So if you do that measurement, then measure W, then you get you get this rho W, which is the 2x2 density matrix of W, and the probability is just the probability of this PAK. So now if I'm calculating the trace rho W to the n, then you just get some powers like p to the n and 1 minus p to the n. And so you just get some some terms which are polynomials in this one number p. So in the end, the calculation reduced to trace of ZAK rho A to some power. If you expand this, you get power n and lower powers. So in the end, you get something like this. So at the most you have 2n. At the most you have 2n replicas here, and then so this power m is outside the trace. Right? So then now if I do the gravitational quantum integral, it's natural to assume to guess that the dominant saddle point is given by replica wormhole connecting these different copies. Consider connecting your physical copy and these simulated copies. I mean, it's like I'm calling them simulated copies because they are defined in the operator ZA. I don't need any quantum entanglement with my physical system to create this ZA. In principle, if I know exactly what's the initial state of the black hole, I can simulate that with a big computer, and then I just get the ZAK. What I need is the knowledge about the system. I don't need any quantum entanglement. But so if I have this ZAK, then I'm connecting them. Then I get this in picture is something like this. So it's like I have this. So the nth linear entropy of W reduced to this expectation value of PA. I should write a K here. Reduce this to the expectation value of PAK, and then to some power n, and then to some power n, to n. So if you write out the PAK, it contains this simulated part of the geometry. So like it has its own geometry, and then there is wormhole connecting between the physical system and the simulated system. But there is no wormhole connecting like the different physical copies. Like you don't have a wormhole like this, which is what happened when you have the ordinary, like if you are calculating trace row A to the n, then you have wormhole like that. So this is why we get this contradiction earlier, because when we do that Paz-Negro earlier, we were assuming that there is a smooth geometry, which could be just the two copies, or it could be like a wormhole connecting these, but we didn't consider the case where you could have a geometry that even changes the boundary condition. Like the geometry itself even now has this wormhole connecting to something else. So it's not even some smooth geometry connecting with the flat space. That's the assumption. That's where the assumption missed this point. So so this is, and of course this is similar to what happened in other constructions we know. Like if you do the path map, you also get this kind of connections between the simulated copies and the original geometry. I think if you do other constructions like the modular flow, it's not clear how this happens, but you see, like if you, imagine if you do some ensemble average, you will get similar things that couples the system with the operator you introduce. So really this ZAK I introduced is just a different way to do that. It's a little simpler than the path map because it's asking a simpler question. It's just binary question, like is it rho or sigma? And then I'm doing this to tell. So it's a simpler question, so it's a little simpler construction. But the point of that contradiction is saying like this is not only just true for these several examples, but it's generally true that any measurements that learn a little bit about the interior will always have this feature that the dominant saddle point is not a smooth geometry anymore. Any questions?
I guess one could probably connect that to maybe some statement about the somehow the dimension or
The dimension?
some other properties of the operator. I mean, if one had an operator that deciphered this interior bit, then maybe one could. I mean, is there a field theory way to characterize the this property of the operator? So you've given kind of a gravity way of characterizing it, but it'd be interesting to say, therefore, it has to have like this dimension or this complexity or something.
Yeah, that's exactly. Yeah, I think that's a very interesting question. Yeah, that's exactly what. Yeah, I'm curious about. I don't know, and I mean, like previously, sometimes I hear. I mean, I think sometimes I got the impression that when we think about a large measurement like this, like a measurement that knows about the interior, people may think that it's large because it's like it has to project on many qubits. Like you have to like do a projective measurement that projects a lot of space. But here, like the example here is you actually only extract like 1 bit information from it. Like I'm just learning 1 bit information, but even that you can't do without changing the geometry dramatically. So so it's not the amount of information I learn that's important here, and I'm not sure if it's. I think it's also not the energy you use, so it's not clear. It certainly requires a high complexity, but so far it seems like the key is the correlation with the macro states. It's like it's really that knowledge about that particular macro state. So that's why I call it miracle operator. It's like a hidden key. Like if you know it, then you can do this quickly. But like if I have an SYK model, then presumably, if I apply this operator that's for a wrong SYK model for a different J coupling, then it probably will just behave like an ordinary operator. But if I apply it to that particular coupling, like particular state correspond to the black hole macro state, then it will suddenly give you a big deviation from the original state. Yeah, so maybe I will use a few minutes to discuss the last part, which is the implication to the firewall paradox, and this is for that particular construction. So yeah, so now if I take this particular construction of ZAK, which is the odd power of the difference of two states, this is just one particular way to get information from interior. But the advantage is that it's simpler than the path map, so I could hopefully see a little more clearly what happened to these setups that we try to probe in the firewall paradox. So now I'm going to consider two setups. One is try to see if I can destroy entanglement across the horizon. So this is when I have the stated row which has an entangled pair of B and B tilde. I put a minus here because I want to consider the pair that's up down minus down up. Like the B has a spin 1/2 and it has up down minus down up. Okay, so now I want to say, okay, now the B tilde is in the entanglement island of A. So I should be able to do a measurement in A that tells about spin of B tilde. And if you do that, then you should destroy the entanglement between B and B tilde. And then, so now the question is, okay, can I consider a setup where first I do a measurement in A that tells me about spin of B tilde, and then I have a infalling observer X that carries that information and come in and check whether the B and B tilde are still entangled. So the way to do that in this in the current setup is I consider two states, sigma up and sigma down, which are states with a pure state in the interior. So sigma up has spin up particle here, and sigma down has spin down particle. So these are the two states which are only different a little bit, and we can apply that discussion and define the ZAK using these two states. So this ZAK is like the, I mean, after analytic continuation, like the optimal operator that distinguish the particular two states with spin up and spin down. So you can think of them as, you can think of this operator as like a spin Z measurement in the interior. Now, if I evaluate that, I'm calculating the trace of ZAK. I'm calculating the trace of ZAK with my state rho minus. So rho minus is like different from both of them. It's a entangled, it's a superposition of the two. But I can apply that operator, and then I get this trace. So now I'm considering a universe. I'm considering that there is this infalling observer in every replica. So I have this replica calculation where I have multiple copies of the universe, but one of them is my physical copy rho minus that has this entangled pair, and the other copies are the ones that has a product state. It has up or down. So then, but remember, every copy should have this infalling observer. So now the question is whether infalling observer will succeed or fail in checking the entanglement between B and B tilde. And the answer is it will fail. It will see that B and B tilde are not entangled. And the interesting thing is there is a topological reason of that, because if you have this infalling observer, which, okay, first measures the spin of B, and then goes in to measure the spin of B tilde, then in this replica calculation, what happened is that the observer is not seeing B and B tilde in the same copy. So I have this physical copy where I have entanglement between B and B tilde. And then there is this replica wormhole. So my B tilde goes to a different copy. So when my X falls in, it sees the B, and then it sees B tilde from another copy, which is the green one here, which comes from which is a pure state coming from another copy of the universe. So that's why like you will fail the check of entanglement. So the infalling observer X is going to say, okay, I see a firewall. So it's consistent with the fact that the measurement outside has destroyed the entanglement. Any questions? Yeah, so you see like the key thing is that there is this topological obstruction. Like when you go around this branch cut, which is the boundary of I, you actually like there is a closed loop between X and the trajectory of the particles that tells you that you don't meet the same partner. And then you can apply the same setup. You can apply the same idea to a different setup, which is the entanglement checking. Like instead of like doing a projective measurement on B tilt that destroys entanglement, I can consider a case where I want to check outside. I want to check outside whether B and B tilt are entangled. And the way you do that is you need to enlarge your region A so that B is also part of it. So then sitting in that region A, which includes B and also include B tilt because B tilt is in the island, now you are able to introduce a projective measurement that test tell me that B and B tilt are entangled. So to do that in this setup, we define two states. We define two orthogonal states which correspond to orthogonal entangled states, like up down plus down up or up down minus down up, like two of the four Bell states. So by defining these two states and then take the difference to some odd power, that's an operator that when you measure it, you tell me whether the state is the up state, the plus state, or the minus state. So I'm simplifying the question to a binary question. So I tell you that there is an entangled pair between B and B tilt, and it's either plus or minus. And then you do this measurement, you tell me it's plus or minus. And then with that information, now you carry that information and fall in with this infalling observer X. And then the question is whether X is going to succeed checking, like X is going to try to check again whether entanglement between B and B tilt is in the state plus or minus. Then ordinarily we would say it's going to fail because you already checked that B is entangled with A with the earlier radiation. So you shouldn't be able to also check like the infalling, like B and B tilt are entangled. And even if we consider the setups where B tilt is part of A, for example, this final state projection model, there is still some problem. Like there was earlier discussions where there is a final state projection model where you can see how like through the final state, degree of freedom in the interior will be mapped to, like B tilt will be mapped to A. There is an isometry from B tilt to A. But in that setup, there was a problem pointed out by Raphael Busso and Douglas Stanford, where they say like if you do the measurement in this way, in this order, like you first check entanglement between B and A, and then you check entanglement between B and B tilt, then it's not going to succeed because the ordering is problematic. Like the first check will destroy the second check. And recently Ahmed has a work which I saw his talk a few months ago. I think that's so he's saying like in this case the entanglement checking could work because you're creating new copies of universe. I think that's related to this discussion here, although I'm still not sure exactly what's the correspondence. So in this in going back to my setup, in this setup here, what happened is that I can consider different copies, and then so the green and the red are two different replicas, and then you send in an infalling observer, and now you see this is different from the case where you measure the spin because now B must be part of A. So when the infalling observer sees is that B and B tilt both go through the branch cut between different replicas. So when you go in, you actually see B and B tilt from the same universe, from the same copy, because both of them go through the same replica wormhole. So that allows you to check B and B tilt entanglement and conclude that they are indeed entangled in that particular state. So both entanglement checking for outside and inside can both succeed. Although the other setup earlier tells you that you can do some measurement outside that destroys the entanglement. Yeah, so the hope is that this could remove some ambiguity in the discussion. Like as you see, like in like when you in a toy model, you could have different conclusions based on different ways, different assumptions. But hopefully here, like the setup contains everything, and you don't need to assume whether the measurement will succeed or not. Of course, there is still problems because like I'm assuming. I mean, there's more fundamental problems like the infalling observer. When you do a measurement, how do you tilt here? Because everything falls into the singularity. So I'm not addressing these kind of questions. then I'm just assuming that the infalling observer will work like just like an exterior observer, because there may be still a long time after the seed is BQ. So I'm just assuming like if B and BQ seen by the observer is indeed in this entangled state, then X is going to tell that. X can tell that without worrying about like what happened after that. Yeah. So that's the whole everything I want to say. And yeah, I mean, I think similar, it's just like what Mark asked earlier. There's many questions related to this, like how many such operators exist, and what do we really require? Like what kind of operator can really introduce this kind of wormhole connecting to a simulated black hole? And also, like if I don't rely on the replica trick, I really don't know what it means to have this wormhole connecting to a simulated black hole. So it's, I think we have that paradox that we actually only understand with replicas. Okay, I will end here. Thanks.
What questions for Xiaoliang?
Yeah, I guess I was wondering how can many of the things you said be carried over so there's also just the kind of version of the firewall when you don't have an asymptotic region, you don't have the evaporating black hole. I mean, just with ADS CFT, you can think of various pure state black holes and ask whether there's some smooth geometry behind the horizon and how do you diagnose it and so forth. So do many of the things you say carry over to that situation as well, or?
I think so, because the one norm distance calculation should apply directly to the ordinary ADS CFT case. Like if I do the derivation of Ryo-Takanagi formula, and so you have the boundary, there's the twist operators there, and then I'm just going to do that for the trace row M and sigma to M, and everything should continue to apply. Yeah, so I think it will be similar to here.
Mm.
So where the entanglement island will be just replaced by entanglement wedge in the ADS-CFT. But to be honest, I'm still confused by some basic things there, because I'm going to conclude, if I do that, I'm going to conclude that. So yeah, so let's say if I do this discussion in the ordinary, just the most ordinary ADS-CFT, and then I have a region A here, and then this is my entanglement wedge. Then if I do this calculation, I get like rho A minus sigma A is the same as rho AI minus sigma AI in the bulk. So let's say this is graph T. But that implies that if I take a small region, like let's say a small part of A, and let's call that W, then that W will follow the same discussion we had. It's going to have no, I mean, it has a small entanglement wedge, but for something outside the entanglement wedge of W, if I apply a local unitary here, let's say if I apply a local unitary here, then that's going to not change the state of W. So it's not surprising. I mean, you have a bulk, you apply a local unitary there, it's going to not change the density matrix of a small region.
Yeah.
But then the same problem happens. Like I could do a measurement on the bigger region and send the information there. I think it's similar to the discussion here. It probably just tells me that whenever you do that measurement, like if I do, yeah, so like I could ask the same question in the ADS-CFT case, which is just you have this region A, and then I have a local unitary spin flip here, and then I ask, okay, what measurement I can do on A that knows about that message. then it seems this is telling me that that measurement has to also create this kind of wormhole. But on the other hand, the state, on the other hand, there's HKIL kind of reconstruction. So it seems like I don't need a very complicated operator. So that's actually
Right.
a point I'm still confused about.
Okay. Yeah, I guess okay, that's confusing. I was thinking about the more complicated situation with some single-sided black hole, like just some pure state, and then the operator or the U behind the horizon.
Thermal field double projected on one side.
Something like that, yeah.
Yeah. That should be very similar to the discussion here.
Right.
Just a comment in the regular ADS CFT case you're drawing on the right there, it seems important that to actually do that measurement and put the measurement result in this subregion W would take some time. Like you couldn't do that instantaneously. And I think that partly addresses the tension that you're thinking about.
Yeah, it's like maybe in that case it's easier to see why it's a problem, because there is no singularity. So before I'm going to do that, that signal already come out directly. Yeah, like before I measure the whole A and then put the information in the slot, I could just wait and then and just wait and the information comes out.
Yeah. Like you'd have to measure all of A and maybe you can get the result to like the tip of the diamond, but that is in the future of UP, and so it's okay.
Yeah. So really that's the special thing for the interior region, that like in the effective causal structure of the quantum field theory, you never see it goes out. That's the part that goes wrong when you do this measurement.
Does this construction have anything to say on sort of the idea of the frozen vacuum inside the black hole? Does this constrain that in the
frozen vacuum? Oh, you mean like anything I did in the interior has to be undone?
Yeah, that there's some ambiguity in what the state is or the operators are in the interior.
Yeah, so I don't know how you avoid that possibility, but I think the whole discussion here is assuming you don't have to do that. So it's like it's assuming like there is this mapping, like when I have the saddle point M, then there is this Q of T space rho for, let's say, for the whole system, and then there is this mapping from that to the. Let me just write the Q of T. There's a mapping from the Q of T states to the states of the QG states, which are the states of the boundary and path. And let's say if I flip the spin in the interior, it corresponds to different states. So all these are saying like the interior is not frozen. Like I can do a measurement outside to change states in the interior. So but I'm not quite sure. I mean, I know there's this discussion, but is there some argument that says you have to undo anything in the interior?
No, but I think I understand. So you sort of assume a fixed map between the QFT and QG Hilbert space, and I think that answers my question.
Yeah, I think that's kind of that's an interesting question. So like when we discuss path map, then then it's a map. It's a map that should apply to all the states in certain code subspace. So then I think the frozen vacuum question is like whether there is an ambiguity in what map you choose, and whether some excited state in one setup in one choice will look like a vacuum state in the other. And here, instead of asking for something like a path map, I'm just asking about like two states, and then whether their one norm distance is preserved. And that seems to be more kind of independent from that question. like without explicitly constructing the bulk boundary mapping, this is showing that that mapping exists because I preserve the distance between states. Yeah, but it's interesting whether that, I mean, that doesn't mean the mapping itself is not ambiguous. I don't know if that suggests, I mean, you could have a family of mappings, each of them preserves the norm. So I don't know if it's exclude that.
Should we thank Xiaoliang again?
Thank you.
Thanks for the talk.
Thanks very much.